So we could say, not too surprisingly, that many compounds have bonds that are partly ionic and partly covalent. And of course, what that means is a little bit fuzzy, because the covalent part of it means a pair of electrons must be shared, or two pairs, or three pairs, as we saw. And the ionic, the usual ionic bond, we talk about an electron being transferred, or more than one electron being transferred completely. So what happens in the case of many compounds is that, let's say a pair of electrons is shared, but it's not shared quite equally. One atom gets a little more of its time than the other. And since electrons are negatively charged beasts, the atom that gets a little more of their time will have, on the average, a little bit more negative overall charge, because those electrons are negative after all, than the other atom. So what I would like to point out to you is there is what amounts to a continuum in bonding, from purely covalent to purely ionic and a whole bunch of stuff in the middle. Okay? And the extremes are pretty easy to understand based on what we've said so far. I will come back to this diagram later, but I just want to point out to you here that if we look at a three-dimensional plot of the electron density of a purely covalent bond, presumably that between the two hydrogen atoms in H2 is about as purely covalent as we're likely to get. The distribution of the electron density has two maxima over the hydrogen atoms, directly above them. But it also has, if you look, a region of electron density in here between the two atoms that is significant in its quantity compared to the electron density around the hydrogen atoms. And although fluorine molecule has fluorine atoms that have a lot more electrons, and so the top of these things are cut off so they won't damage the top of my laptop here going up so high, you can see that there is here another region of sort of shared electron density. And that the size of these two peaks is about the same, so that's equal sharing, more or less purely covalent. But if we then look at the molecule that can be thought of as having these two molecules as its parent, HF, you could see there's an electron density peak right there, and then a great big one right here. Okay, so there is shared electron density. There's no doubt about that. But it should be clear that these two atoms don't have anything like equal electron density around them. And this is one of the things we're going to focus on today. The ability of an atom in a molecule to attract the electrons that it shares with another atom, of course, is called electronegativity. And there are more electronegativity scales than you can shake a stick at, but we're only going to mention one of them, and that's the one due to Linus Pauling, since it is the one that we encounter most frequently. Okay? And electronegativity, as Pauling coined the term, I guess he coined the term, I abbreviate as EN, is the ability of a covalently bonded atom to attract the shared electrons. In other words, to force them to spend more time in the vicinity of that atom, which has a high electronegativity, than maybe the other atom, which doesn't. Now, Pauling based his concept of electronegativity on bond energies. And we are given to believe that it started with him thinking about the fact that the bond energy for a molecule like HF is not anyways close to being equal to the average of H2 and F2. If all there was to the bond energy of diatomic molecules was the covalent part, it might be reasonable to expect that HF would have a bond energy somewhere between 432 for H2 and 159 for F2. But if that were the case, that averages out to about 295. We would predict for the covalent bonding a bond energy of HF a little less than 300. But in the laboratory, the actual bond energy of HF is 565. It is the most ionic molecule that we're likely to come across, according to Pauling. That is to say that the difference in the bond energy that's actually found and the average bond energy here is the greatest for HF of any molecule that we are likely to come across. And Pauling is about a difference of around 270 kilojoules per mole. Pauling said that amount of energy or strength of the HF bond is owing to the fact that it has a significant ionic contribution to its bond strength. Okay? And the ionic contribution is a measure of how much distortion there is in the sharing of the pair of electrons that make up this bond. In other words, how much it is drawn towards one atom or the other. Well, it's drawn towards the fluorine. You probably are aware of that. And to whatever extent that happens, this makes the bond here is said to be polar. Polar bond, meaning that instead of having a very smooth and even distribution of electron density, that there's more electrons spending time over one of the atoms and less over the other. And to the extent that that happens, of course, and that electrons being negative, then there will be a sort of a negative pole and a positive pole to such molecules. And we call that polarity, the presence of poles. The direction of the polarity, of course, is determined by which atom has the higher Pauling electronegativity. And the magnitude of the electronegativity difference is a sort of a direct link to how much ionic character there's going to be there. So if we look at HF, for example, the delta electronegativity could be calculated by taking the absolute value of the electronegativity of H minus the electronegativity of F. And that magnitude, according to Pauling, would tell us how polar the HF bond is expected to be. Okay, so Pauling thought a lot about this, and some of his extensive work is surviving in our study of chemistry today. And what Pauling found was that fluorine, because of other measurements and observations that he made, fluorine clearly attracts the shared electron pair more strongly than hydrogen. And so the electron pair spends more time closer to the fluorine, and the unequal sharing of the electrons makes the fluorine end of the molecule partially negative, not a full negative charge, part of a negative charge, something between 0 and 1 charge, and the hydrogen an equal amount with a positive sign on the other side. Now, I suspect that you've seen these things somewhere along the line. And what Pauling said was, it is these charges that make the HF bond stronger than it would be if it was purely covalent in its character. It's just like an ionic contribution, if you will. And there's a good deal of discussion about partial ionic charges and percent ionic character in your textbook. So the ionic contribution to the bond energy of a molecule is somehow proportional to the difference in the electronegativity between the atoms in the bond. Okay. If we carry that forward, this difference has some periodicity to it. For example, if we look at how the bond energies, the actual bond energies and the average bond energies of the parent elements decreases down a group, and if we take group 7A, this is the expression for that difference, delta here. It's the bond energy of HX minus 1/2 of the sum of the bond energy of H2 and X2. H2 minus, there's an error right there. There's an error. That should be a positive sign. Would you please fix it for me? And I apologize for the error. It should be plus. 1/2 of the sum of the two makes the average. Okay? Everybody got that fixed? Good. So if we do this for the halogens in group 7A, and we calculate the delta value, for HF, as we saw a few minutes ago, it's 270 kilojoules per mole. HCl, it drops down to 90. HBr, down to 50. And HI, it's almost nothing. So Pauling looked at this and he said, well, in the case of HF, fluorine must be much more negative, much more electronegative than hydrogen. And chlorine is more electronegative than hydrogen, but not as much more as fluorine is. So the electronegativity of chlorine must be a little bit less than that of fluorine. And bromine must be a little less yet. And the electronegativity of iodine looks like it's almost the same as the electronegativity of hydrogen. Well, Pauling looked at a bunch of these things, and he came up with a way, after assuming that fluorine was the most electronegative element and that its Pauling electronegativity was 4.0, he developed a whole scale. Okay? The scale was based on these differences, and we're going to talk a lot about it as we go along here, a little bit now and more later. He derived relative electronegativity values based on fluorine as 4. Okay. If you ever are in need of a little science project, he worked at Oregon State University at the time he was doing this work, and they have collections of his notebooks, as I think I mentioned to you before. And you can go and actually, they've scanned in the actual notebook, and if you can read his writing, there's a lot of interesting things there. So let's look at the values. Here is here are the electronegativities of the main group elements, all except for hydrogen here. And I think you can see that there is, the way he defined it, a real nice, simple, increasing trend from bottom to top of each one of the groups, and also one from increasing from left to right across a period. And there aren't too many places, if you stick to the main group, where these trends are violated. So remember these trends, increasing up a group and across a period. That makes the nonmetals more electronegative than metals. Over here, these are metals, and these are the nonmetals. You notice there are no electronegativity values in the Pauling scale for the noble gas elements. Why would that be? He says they're inert. They have no, they don't form hardly any, maybe a handful of exceptions, diatomic compounds. And the bond energies are usually very, very small indeed, and these things are very troublesome to work with. So he doesn't have any. Some of the other scales do have electronegativity values for the noble gas elements, and they turn out to be surprisingly large. Helium, for example, is thought to be larger than fluorine if you believe the method that was used. Hydrogen is a trick that you need to watch for. It falls in between boron and carbon. Its value is about 2.1 or 2.2 right in there. But if later on we're going to look at the polarity of bonds, and if we look at the polarity of bonds involving hydrogen, like CH bonds, for example, the electronegativity difference between carbon and hydrogen is pretty small because, as I said, hydrogen falls in between boron and carbon. Now, the most electronegative element in the Pauling scale is fluorine, and the least electronegative element is cesium, among the stable elements at least. And so that would be a pretty good indication of why MX compounds are ionic. Because at least to the extent that electronegativity has anything to say about it, the M's over here and down here are much less electronegative than the X's that are over here. And one of the things that you would expect to be the case is if we're forming ionic compounds like this, there should be a big electronegativity difference, and we'll come back to that in a few moments. This is the periodic table in electronegativity, at least most of it, where the values are known. And I just show it to you to show you that the transition elements and the intertransition elements have electronegativities that don't change very much, and it will be our practice to ignore these elements when we're talking about electronegativity, just because the differences are so small. For example, if you look at iron, cobalt, and nickel, they all have 1.8 Pauling electronegativities. And they in some cases, they actually go up as you go down. So there aren't any simple trends, and there are not many big differences. So let's make life simpler for ourselves, and we will focus as much as we can on the main group elements here, here. And notice they did stick in hydrogen between boron and carbon there for us to help us remember. Questions? Okay. Now, as we look at this, the differences in electronegativity values is where we have to focus. And I wanted to pick out a few of them, give you what they are for certain kinds of compounds so that you'll be comfortable with this. So this is a page you don't have in your notes because I just want to scribble down a few things here. So we're going to look at delta En, the difference in electronegativities, and I'm going to look at three compounds: lithium chloride, and hydrogen chloride, and dichlorine. Okay. Delta En for lithium chloride is absolute value of 3.0 minus lithium is 1.0, more or less. So 3.0 minus 1.0, that will give a delta En of about 2. HCl, we have 3.0 minus 2.1, so that's about 0.9. Cl2, we have 3.0 minus 3.0, and so this is 0.0. Now, the general rule for using delta electronegativity to give us a feeling for the bonding character of the compound is that 50% ionic character marks the line between ionic compounds, which are higher than 50%, and covalent compounds, which are less. If you look at these particular compounds, I looked up the percent ionic character. And for lithium chloride, it's in the neighborhood of 70%. And for hydrogen chloride, it's in the neighborhood of 20%.
Is that 10 or 70?
70% and 20%. And of course, chlorine, it's approximately 0%. Now, the line of demarcation for delta En is somewhere around 1.8. And this is a largely unsupported value. It's a little bit arbitrary. But it would account for, it would indicate something like 50% ionic character. Okay? And so you could see somewhere in here, between 70% and 20% is the 50% value, and 1.8 is, of course, between 0.9 and 2.0. So up here, these would be ionic, mainly ionic. And so lithium chloride would fall into that general category. And down here, below 50%, this is mostly covalent with some ionic. And down around 0% is nearly all covalent. Now I have a graph later to show you, but this gives you a sort of a thumbnail sketch of how delta En connects to whether a compound is mainly an ionic compound or whether it's mainly a covalent compound, which is what we're trying to do. Questions on this? There is another arbitrary thing at 0.4, which I never saw the use for, in the sense that it says below 0.4, the bonds are almost completely covalent. I think what they mean is below 0.4, the bonds, the covalency predominates and the ionicity is small compared to it. But I think it's a continuum. I think you should look at it as a continuum. And although I can see why 50% sort of makes sense, there isn't any sharp break right there in the properties of the compound. If we look at these molecules that are made up of atoms with different electronegativities, we get into a lot of very interesting kinds of molecules. In biology, for example, polar molecules with polar groups in them, polar bonds, play a very important role in how a whole bunch of different biological processes occur. And this runs all the way from heredity to the processing of food stuff. Okay. So, if atoms with different electronegativities bond, and the bonding pair is therefore not shared equally, then we know, as we said before, the bond will have partial negative and positive poles. And we will call it, therefore, a polar covalent bond, in that it has covalency, but it has polarity due to the fact that the electrons in the bond are not shared equally. And this is not limited to single bonds. A carbon-nitrogen double bond is a polar bond, just the way a carbon-nitrogen single bond is. And we use delta plus and delta minus to indicate the partial ionic charges that are present. We can also use something that's called a polar arrow, which points from the less electronegative atom, hydrogen here, to the more electronegative atom, fluorine in this case. And that shows that it's a polar molecule and which end is more polar. And we could also use the delta plus and the delta minus. Now the magnitude of the polarity, and therefore the magnitude of delta here, does depend on delta electronegativity. I go back to this picture again. The molecules that have the same electronegativity in both atoms, you can see have a symmetrical distribution of electron density, whereas ones that have delta En greater than 0 have an unsymmetrical distribution of electron density, and you could write a delta plus here and a delta minus here. And if we look at a typical, well, this is not quite typical, but if we look at a predominantly ionic compound like lithium fluoride, you can see there's a big difference in the electron density for these, the lithium ion and the fluoride ion. And there's not very much shared electron density here, but there's a little bit. And we take from this that even very strongly ionic bonds have a little bit of covalency in them. Okay? And if you go on in science and you look at the quantum mechanical treatment of H2, even H2 has, according to that treatment, a little bit of ionic character to it. Okay, our next task here is to rank bond polarity and predict the direction. So first of all, we indicate the polarity of these three bonds, NH, FN, and ICl, with a polar arrow. And then we'll rank the following bonds in increasing order of polarity, HN, HO, and HC. Well, if you look at where hydrogen is in the periodic table, you know that nitrogen is to the right of where hydrogen shows up, even if you put it where it is in electronegativity terms between boron and carbon. Nitrogen is still to the right, and the trend increases, so nitrogen is more electronegative than hydrogen, and the polar arrow then would point toward the nitrogen, and this would be a delta minus on this side, and a delta plus over here. If we look at the NF bond, or FN bond, if you will, fluorine is more electronegative at 4 than nitrogen at 3, so we're going to have delta minus over here on the fluorine side, delta plus on the nitrogen side in an FN bond. And iodine has an electronegativity of 2.5, just a little bit above that of hydrogen, actually. Chlorine is 3.0, so iodine is less electronegative, and the arrow will go from the iodine. The cross on the tail here means this is the positive end, and the chlorine will be delta minus. Okay? If we look at the electronegativity of carbon, nitrogen, and oxygen, all of which are in the bonds to hydrogen here, carbon is the least electronegative and oxygen is the most, and so the OH bond is going to be the most polar and the CH bond is going to be the least polar. So the order of increasing is CH less than NH less than OH. Questions on that? Okay. Now, what I have left to do is to show you this diagram. I thought I would get a little bit further today, but delta En, we stress, is a measure of the polarity of a bond, and that could be in terms of partial ionic character. And we talked pretty much about this. If delta En is greater than 1.8, the bond is mostly ionic. If it's 0.4 to 1.8, it's polar covalent. covalent bond that has some polarity to it, and less than 0.4, it's mostly covalent to purely covalent. 50% is the breaking point between mostly covalent to mostly ionic. And here is the diagram, and the dotted line across is 50%. The vertical axis is percent ionic character. The horizontal axis is electronegativity difference. Now notice here, notice something important. Two things, and then I'll let you go. First of all, the 50% is arbitrarily set. And you can see that lithium iodide is only a tiny bit above it, and HF is only a tiny bit below it here. So when you see things like that, you know we're talking about an estimate. But up here, above the 50%, there's a grouping of compounds whose properties clearly show they are ionic. And down here below, we have properties that are molecular, meaning that the substances exist as uncharged molecules. And as we get further and further down the line here, electronegativity difference of 0 leads to about 0% ionic character. All right, some molecules, such as chlorine, appear to have 0% ionic character by this scale, but none has. The second point is none of these has 100% ionic character. They top out at about 85 or so. Questions on that? Okay, I leave you with the idea that electron pair sharing occurs to some extent in every bond.